Good morning, good afternoon, everyone. So this is the Center for Signal and Information Processing seminar series, and this is the last cinema talk, and usually hosted by DSP group at Georgia Tech ECE. The group chair is Professor Gassan Ajiba, and today we are honored to have Dr. Chile. So Chile is an associate research scholar at Princeton ECE department, working with Professor Jason Lee. So she received her PhD from University of UT Austin, and Dr. Chile had both solid theoretical background and received a lot of reward from the machine learning community, including outstanding dissertation award and Simmons Berkeley Research Fellowship Award, and a lot of award in this community. So, Chi, please have your presentation.
Okay. Hi everyone. Thank you so much for having me today, and thank you for the introduction. So today I'm going to talk about my not so recent work on some theoretical understanding about representation learning. So I guess since this is a small crowd, you can always interrupt me if you have any questions. And this is joint work with my wonderful collaborators, and they are mainly based on my two works published on this year's iClear and the NERDS. So you can find the links of the paper here. So like many other talks you might heard from, this work is also motivated from deep learning training. You see that deep learning succeeds with abundant labeled samples. However, our goal of intelligence is to mimic how humans are learning. And you can imagine how people are learning. We don't actually need so many labeled samples. What we do is we observe the world and extract some useful features. For example, here, to distinguish different types of dogs, we can extract ear shape, etc. Then those useful features will help us to fulfill some future tasks without many external instructions. In other words, we don't need so many labeled samples. And we want to argue that the training process of deep learning can do similar stuff. Like from the input, we also want to do some representation learning such that it can help us to understand the features, such that it can do some future tasks with not so many labeled samples. And there are some important properties we want to seek in a good representation. First thing, of course, it is that it is something we can learn. It can be identified from the neural network training. And second, it can help us to reduce sample complexity. It can help us do something like the few-shot learning. And it can even be learned from unlabeled samples. Like it is common practice in NLP tasks, we can mask some words and learn it from the other part. And finally, we hope that the learned representations can transfer to other tasks or domains. This is very important for the safety issues. We surely hope that the representation we learned from a sunny day will transfer well to a rainy day. Yeah, these are the properties we want a good representation to have. And of course, learning or understanding representation learning is very important because there are so many success stories about it. Like in any domain without enough data, or in the domains where the data annotation is very expensive, we need a good representation to help us reduce sample complexity. Or even in applications with a lot of labeled samples, it is worthwhile to benefit from more unlabeled samples. And in language models, transfer learning, meta learning, reinforcement learning, etc. So it is urgent and very important to understand representation learning. And the purpose of this talk is not to develop some new algorithms, but we want to theoretically understand representation learning from the perspective of statistical learning theory. So what it means is that it should be based on some correlation of the data distribution or the relation of the training and testing tasks. And in this talk, we will focus on both supervised pre-training from multiple related but different tasks and the self-supervised learning. So this is the setting or the focus of the talk. So now let's move on to the first part, which is supervised representation learning. The procedure I'm looking at is very simple. So we have the source domain and the target domain. In source domain, we have one or multiple different tasks, and we learn the prediction function, which is composed with representation and some task-specific predictors. The representation part is just the first few layers of the neural network, and we will transfer it to the target domain, use it as fixed feature, and then we only learn another layer on top to do some future predictions. And hopefully this procedure will work, which means that the representation is good enough such that a single function on top can help us to fulfill future tasks. And also, since we only learn the last layer, the samples we required will be very much reduced. Since we are looking at some theoretical understanding, I need to first introduce some notations. Let me denote X as the input data. I will look at T different source tasks. And for each task, we have N as samples. And this X, I will use this small t to index different tasks, and this small I to indicate different samples. And the procedure, as I described, we will learn a representation function on top and the task-specific predictor. So this one is indexed by t on the representation to minimize the distance between the prediction on X and the label Y. And we will have one target task, and it has NT samples. And we are interested in the few shot regime, so the number of samples for the target task is smaller than the number of samples from the source task. And let's represent the function class for the representation function to be capital B, and the function class for the last layer as G. And usually the complexity for phi is much larger than the complexity of G. And our learning procedure in mathematical language is like this. So we minimize the distance between each label Y and the prediction. And we learn this representation phi on top of each input data. We use it to be the shelled representation for the target task, and we only learn the last layer on top. Is there a question on the setup? Okay, so let's move on. In theory, the key question is actually how to quantify the task similarity. So you should imagine if all the tasks from the source task have no similarity to each other, no relationship to the target task, then there's no way you can learn a useful representation. And in prior work, they assume that tasks are sampled from the same meta distribution queue. So they assume there is a queue, and we sample each distribution for each task, PT, from this meta distribution. And then the data for each task can be sampled accordingly from each PT. And no additional assumptions are made. So in this case, prior work can get a generalization error like this. So they show that the risk of learning the whole procedure on the target task will be upper bounded by a representation error of this form plus the estimation error of this form. So basically, the representation error captures how well your representation can predict the y. And estimation error is because you are learning the last layer with finite samples. For this problem, you can imagine because you are not making any additional assumptions, it is very unclear what information is being transferred through different tasks. So what it is doing is like we sampled T different tasks, and you can view each task as a single sample to jointly learn the information from the meta distribution. So you can see that the representation error scales with 1 over square root T. And the problem is it cannot even utilize the NS samples across different tasks to jointly learn the representation. And this is certainly not something we want. And unfortunately, this 1 over square root T is not improvable without further assumptions. And this kind of result is not aligned with real practice. In practice, even if we have one single source task, it can work. And also, when there are more samples from the source tasks, of course, the performance will be better. So we should imagine that the ideal rate should look like something like this. So the representation error here should be of this form. So basically, we are using all the samples from the source task to jointly learn our representation function. And also the estimation error is as expected, all the number of samples from the target task to learn the last layer. And we're hoping that without such assumptions, such a rate is not attainable, which means like in some perspective, in some regime, this kind of assumption is even necessary. So I haven't talked about how to achieve this yet, but I guess we can all agree that this looks like some ideal rate we are trying to get. Okay, so before I talk about how to attain this kind of result, let's do a comparison. So compared to previous result and what we want to achieve, the biggest gain is, of course, we can pull all the source samples to jointly learn the complex representation. And this is the most important part. And a minor gain, which is important to statistical people, is to achieve a fast rate instead of slow rate. So there's no square root here. But most importantly, of course, is to utilize all the samples from source data. You may see that in previous rate, it doesn't even matter if you have a single sample for each task or you have like 10 to the 8th number of samples from the source task. So now let's look at how to achieve this kind of rate. The key assumption is based on empirical observations. We should assume there exists a shared good representation across tasks. So this is understandable because, like in real practice, representation learning works. That means, of course, there exists a shared representation. Otherwise, there's no way you can learn it, right? And a second assumption, kind of overlooked by many people, is the diversity of the last layer, which is roughly what is the key features that is useful for each different tasks. It is kind of obscure right now, but I will use some concrete examples to help you understand it. So let's see two different tasks. Let's say if the source task, we want to classify different types of dogs. And for the target task, we want to classify cat versus dogs. So this is, of course, a very simple task. It's not empirical work. It just helps us to get some intuition here. So for the source task to distinguish different types of dogs, you can imagine that there are some important features such as ear shape, eye color, coat color. While for the target task to distinguish cat versus dog, there is some important feature like whether it has a whisker or not. But of course, whether it has whisker or not is not identifiable from the source task because it is not used by the source task. Therefore, there's no way we can learn this direction of the features. And mathematical speaking, it is saying that WT plus 1, which is the direction of the feature that is useful for the target task, should be in the span of W1 through WT, which is the directions of the feature that are used from the source task. So this is very important. Otherwise, this direction of feature will be unidentifiable. And you can imagine this, in this case, this part of the feature will not be learned from the source task. I hope this is clear. So with this kind of assumptions, we can first show a first result. So this is a warm-up result on the linear low-dimensional representation learning problem. So we first look at low-dimensional linear representation because it has a very clean geometric meaning. So in this case, the representation function looks like B star transpose X, and B is of the size D times K. So what it does is to take the input X and map it to a K-dimensional subspace. And based on our shared representation assumption, the YT has this kind of ground truth connections to X. YT is equal to theta T star transpose X, where theta T is in the span of B star. So therefore, all the parameters for different tasks lie in a low-dimensional subspace. So this kind of problem was also has been explored a lot before, and we investigated the similar result here. And our risk is something like this. So the representation error here is KD over NST. So as promised, we are using all the number of samples from source task to jointly learn the representation. And what is the representation is this B star. Its complexity is of course D times K, which is the number of parameters of it. And it is very clear what information is being transferred. So basically all the source tasks are helping you to learn this K-dimensional subspace. And then on the target task, you only need order of K number of samples to learn the last layer. But if you directly learn from the target labels, you will need order of D samples. So that is the benefit of the representation learning here. And this kind of result can be easily extended to general low-dimensional representation learning. So here, this representation function phi star maps from input dimension D to output dimension K. And with our assumption that there is shared representation, phi star and the ground truth function is WT in a product with its phi star. In this case, you can see this means that the data can be approximately linearly separable from the K-dimensional representation space learned from us. And with similar assumption, we can show that the generalization error is upper bounded by this form, again composed with the representation error, which is to learn this phi star with an I times T samples. And again, the estimation error is learning the last part, WT, from the label samples from target task. And in this problem, the functionality of this representation is to select the K most important features. And I need to emphasize that in this problem, covariance shift is allowed. So x1 through xt plus 1 can come from different marginal distribution. So this is very practical and really aligns with what we need in meta-learning or the related topics. And also for the source training procedure, since the loss function can be highly non-convex, we actually don't know how to implement it in polynomial time. But of course, on the target task, we are only learning the last layer, so that is very simple and don't have optimization issues. And also the result can be applied when there is a single source task, as long as the features that are used for different different classes are also diverse enough. Then we can show the result like this. So basically we are utilizing all the source samples from the single task to jointly learn the representation. And we are also using all the label samples from the target task to learn the last layer. So this is more aligned with what you are seeing in practice, that you bring a network on like ImageNet and then transfer it to some other tasks. And also the result applies to high dimensional representation learning. So if in particular, we look at a two-layer neural network, which means the representation looks like something of this form. It's a value plus a linear fully connected layer. And on the similar assumption, we can show that the generalization error is bounded by the Rademacher complexity of this functionality divided by square root number of samples from the source task plus the estimation error of this form. You can see for this problem, it looks slightly different than before. If you are familiar with like learning theory, you should have learned from learning theory 101 that the generalization error for like ordinary least square is fast rate, and the complexity of the function class is measured by number of parameters. But here, if we use weight regression or the number of parameters are huge, then we should measure the complexity of the function class by the norm of the weight instead of just counting the parameters. Therefore, the estimation error looks something like this. So this is really aligned with what we know. So all the results up to now are showing in our iClear 2021 paper. And if you are interested, you can look at, you can read the paper for details. So now, do you have any question on the first part? Okay, so let's move on to.
Excuse me, Li. So I have one question about, is the risk upper bound for the risk is a well-trained model does think about is a statistical estimation about the risk. So my question is about how to achieve such an upper bound. If it's maybe it's the best, it's a worst case.
You mean, so in our paper, how do we derive this upper bound?
I think this is very standard, and my question is about do you consider it's a well-trained deep neural network? Is in general it's okay for any general neural network? Maybe it has if there's new data coming, the risk is upper bounded, but such estimation errors plus such as representation errors. Again, can we choose a better upper bound with a lower upper bound? If we can consider some optimization methods. I'm just wondering about this.
Okay, thank you for the question. So first, there's no optimization inside. This is a pure statistical result. It's saying that if we get the optimal model, from training the loss we defined in the beginning, then we can get a risk like this. And I guess you're wondering if this kind of result is tight. So basically, I can only say that it is aligned with what we know, like for each regression, like learning the last layer will look like this. And it is not tight. You can get something that looks very complicated, but it's actually smaller. But I think usually we are interested in some result that looks cleaner and still conveying the message of the risk. I hope that kind of answers your question.
Okay, thank you for your answering.
Yeah, thank you. So if there's no other question, let's move on to the second part. So the previous result relies on if we have different but related source tasks. But if this is not available, then we should think about ways to create pseudo-labels from the input data. So here comes self-supervised representation learning, so which is so popular recently, and we are dying to look at some good theory about it. There are different types of self-supervised learning algorithms, but we can abstract it to look at just the random variables x1, x2, and y. So let me discuss what they are. Like in more traditional NLP kind of algorithms, or BERT, which is more popular recently, the practice is to mask some words and to predict it from the other part. In this case, x2 is the masked word, and x1 is the other part. This similar idea also applies to vision, which stems from a quite older result, which is context encoder, which is just doing an in-painting work to predict some masked image, which also we call x2, from the other part, x1. And the recent state of the art on self-supervised learning is achieved by Kamin He's group from Facebook, which shares similar idea, but they do some more tricks, which is actually in line with our theory. And in this case, x2 is again the masked part of the image, but they do some shuffling, and x1 is the other part. So this kind of algorithms, they predict x2 from x1, or in other words, they construct x2 from x1. And also, like image colorization, they are finding some pretext tasks, which is to predict the color channel from the other part of the image, which is just the grayscale image. So this kind of the first three types of algorithms, they are predicting part of the input from the other part. So we call it reconstruction-based self-supervised learning. And there are also some other types of self-supervised learning, which is like similarity-based. What it does is to like take two views of the image in contrastive learning or in SimScience. They take two different views of the image and ensure that the representation is maximized. Sorry, the inner product of the representation is maximized. So it wants to ensure that the two views of the same image have similar representation. And CLIP also shares similar idea, but in this case, x1 and x2 are different, has different marginal distribution, and x1 is image and x2 is like the paired text. They want to ensure that the images online and their paired text, like their captions, will have the representation, will have similar representation. So their inner product is maximized, but if they come from different contexts, then their representation can be quite different. And the standing point of this talk is on reconstruction-based self-supervised learning, but we will also establish some connection and so show our result can be extended to this kind of similarity-based result. So let's simplify the procedure of reconstruction-based self-supervised learning. So surely we cannot like analyze all the complicated tricks and the engineering part. So the simplified version of reconstruction-based self-supervised learning looks like this. So we take the image and we take some mask part, we call it x2, and the pretext task is to predict it from the other part, we call it x1. And we use this prediction function, we call it psi, and we apply it due on x1 for the downstream tasks. For downstream task is to predict y, in this case to identify what kind of Pokemon it is, y is Pikachu. Then the downstream task is to predict y from x1. Then we only learn a linear layer on top of the representation. So this is very similar to the original context encoder paper. And we want to argue on what kind of assumption this procedure works. By this procedure is working or not, we are trying to analyzing whether it has a small representation error and whether it has small estimation error. So by small representation error is to say that this representation psi x1 can almost linearly learn y. And by small estimation error is to show that we only need very few labeled samples to learn the last layer. Okay. And try to understand this kind of procedure. We are now trying to introduce our key assumption. So for both empirical and theoretical people, the key intuition of self-supervised learning is that we should find pretext tasks that can help us reduce irrelevant features. So now we have two questions. First, under what kind of assumptions between about the connections of x1, x2, and y can we ensure that this learning procedure can reduce the irrelevant features? And the second question is, in reality, how do we ensure, or why do we believe that this kind of assumption holds? So for the first question, what kind of assumption can help us achieve this? Our answer is approximate conditional independence. So basically, we're saying that if x1 and x2 are approximately independent given the label y and some other fine-grained features z. So I haven't introduced what is z. So in the next slide, I will have some examples to instantiate it. Under this kind of assumption, we will ensure that the learning procedure will work. Why? If you look at its Markov chain expression, you can see that if we are able to learn x2 from x1, then it can implicitly encode the information of y and z. Therefore, we have every reason to believe that if we learn this function to predict x2 from x1, then it will also help us to learn y. This is not very clear now, but in a few slides, I will show you a one-line proof, which is very simple, and it will clearly help you to see why this is the case. So now let's try to understand what this assumption means and why do we believe that this kind of assumption holds in practice. So let's look at a very simple example. Let's say we want to do image colorization for photos of desert, forest, or sea. So image colorization is just one typical self-supervised task. Then in this case, Y, the label is just desert, forest, or sea, 3 different types of classes. And X2, the color channel, you can see for desert, average color is yellow or red. And for forest, it will be green, and for sea, it will be blue. So in this case, if you have the information of y, you don't need to refer to x1 to do a good prediction of x2. That is exactly the meaning of x1, x2 being conditional independent given y. So for this kind of image colorization task, we believe that this kind of assumption holds. But of course, this is very ideal, but we can see how it can be relaxed from different cases. Let's see the context encoder task, which is to predict this x2, the image patch, from the other part. So if we know the label y is it is a building, then we might not be able to predict or reconstruct x2 very well. But if you have some additional fine-grained features, like the style of the building, whether it has windows, the color of the door, etc., this kind of discrete features, then you can better and very well reconstruct an x2 with smaller variants. That is exactly what it means that x1 and x2 are approximately independent given y and z. So basically, it's saying that y and some additional fine-grained features are capturing the important mutual information between x1 and x2. And in that case, you will be able, with self-supervised learning tasks, you'll remove the other irrelevant features. So we will first show you a warm-up result with a very strict assumption, which is x1 and x2 are exactly independent given y. And then we will show our mean result with a much more relaxed and realistic assumption. So I can't emphasize enough that this x1 and x2 being exactly independent is not our main result, but it can show very well the functionality of self-supervised learning under this kind of assumption. And also it shows that the better this kind of assumption is satisfied, the better self-supervised learning algorithm will work. Okay, so the learning procedure is first to reconstruct x2 from x1. So we learn this per psi, the representation function, and then we apply another linear layer on top. We learn this last layer. And with representation error is to show whether this optimal W star composed with this representation we learned is close to the ground truth function F star. Which means if we only learn a linear layer on top of this representation, does it still have enough expressive power? And very surprisingly, we can see that this F star, which is among all the nonlinear functions to learn y, the optimal, the ground truth model, is actually equal to W star composed with per psi under this kind of assumption. And therefore, it means that if we learn this per psi from a lot of unlabeled samples, which is almost free, and then we learn a linear layer on top with not so many labeled samples, we can actually well approximate this ground truth F star that is among all the nonlinear functions. That is the best function among all the nonlinear functions. Yeah, and also small estimation error, because you are only learning the last layer, this part is very small, and together the generalization error of learning this downstream task will scale with k over L. K is the cardinality of y. So in this case, we can see that we only need order of k samples instead of a Rademacher complexity of the whole function class to learn y. And in reality, the classes of interest like neural network are very large. So that's why self-supervised learning can work under this kind of assumption. So let's see how we can prove this. It is actually very simple. So notice that the representation function for psi star, which is the optimal function that we construct x2 from x1, is equal to the conditional expectation of x2 given x1. And by law of total expectation, you can write it with this adding another conditioning on y and then average it out like this. And because of conditional independent, then in this case, we can actually remove this x1 because x1 and x2 are independent given y. So you can just leave this conditioning on y and remove conditioning on x1. And in this case, you can see that finally the expectation is only over y, which is discrete and have finite number of values. Then you can write it like this. It's summation of different values of y over the probability of the outer side of the expectation, which is probability of different y condition x1, and the inner product, which is expectation of x2 given different choices of y. So it is of this form. This fx1 is this part p y condition on x1. You can see it is exactly what we want of the final prediction function to predict y from x1, and inner product with this matrix A of dimension k times d2. So you can see that the relation between psi star and fx1 is indeed linear, and as long as A has full column rank, which is not a very restrictive assumption, which is just saying that x2 is correlated with every direction of y. So imagine like a context encoder, x2 is some image patch. Of course, it is correlated with y, with the label of it. And then this f is also linear in psi star. So if you learn this representation very well, you only need to learn a linear layer on top to learn the final f star. Okay. And our main result is with this kind of relaxed assumption. So we don't actually need x1 and x2 to be exactly conditional independent, but the previous result just show how it can possibly achieve similar result if a similar kind of assumption is held. So if x1 and x2, their mutual information is captured by y and some additional discrete random variable, and the remaining part can be quantified by this epsilon ci value. So I don't want to spend too much time to explain how we derive this kind of quantity, but this can be viewed as a quantification of the extra shared features between x1 and x2, not captured by y and some other discrete random variable z. The epsilon ci quantifies the spurious features that is not reducible by self-supervised learning, and it is 0 if exact conditional independence is satisfied. And we show that our generalization error of the self-supervised learning procedure is upper bounded by this kind of result. So the representation error actually scales linearly with this epsilon ci term, which is the irreducible features between x1 and x2. And the estimation error looks like this. So basically, this part is the cardinality of all the random variables of the y, z. And an L is the labeled samples for the downstream task. Epsilon ci is the part of error if you're not learning the first part accurately. So if you only have like finite samples for the first phase, not very important here. But still, you can compare that with empirical risk minimization. So if you learn the downstream task directly from x1, then you will need the label samples to be complexity of the whole function class, while here you only need number of samples to scale with the cardinality of y times z. And also notice that even though self-supervised learning is to predict x2 from x1, but x2 does not necessarily linearly predict y, but psi x1 does. That is because what psi x1 is doing is to reduce the irrelevant features between x1 and x2, so it can actually work better than both x1 and x2. Also, people might be curious whether this kind of result is tight. So basically, we want to investigate whether the generalization error actually scales linearly with this epsilon ci term. And we actually use some simple example to demonstrate it. So to begin with, let's first look at some class conditional Gaussian, which means X is sampled from this kind of Gaussian distribution, which comes from different classes. So Y is inside 1 through K. And this is actually K different mixture Gaussians, and each component of the mixture Gaussian has the mean that depends on Y. And the covariance matrix is identity. And in this case, we split X into two parts, X1 and X2. So X2 is like the masked image and X1 is the other part. And in this case, X1 and X2 are exactly independent given Y, because the only mutual information comes from the mean of the Gaussian component, which is captured by this Y, the indicator of it. In this case, we can see that if we compare self-supervised learning procedure, which is to first learn the representation for psi x1, and then to learn a linear layer on top, then the generalization error is much smaller than if we directly predict y from x1. So this is something as expected, not surprising. But the second part, we also show what happens if only approximate conditional independence is satisfied. So in this case, we carefully design the covariance matrix so that it is indexed by this alpha that is just a rescaling with epsilon ci, such that when alpha equals to 0, this means x1 and x2 are exactly conditional independence, and when alpha equals to 1, then x2 fully depend on x1. And we also do similar experiment, and interestingly, we can see that that the generalization error indeed scales linearly with this alpha, so scales linearly with epsilon ci. And we can see that when alpha is large enough, meaning that x1 and x2 indeed have a lot of shared information that is not reducible from the self-supervised learning procedure, then you might as well just use x1 to learn y, and the self-supervised learning will fail to benefit you. And indeed, generalization error scales linearly with epsilon ci, as our theorem indicates. Okay, and also very importantly, our analysis can also be connected to the other very popular self-supervised learning algorithms like SimScience. Because like before, we only learn for psi x1, the representation from the average, the mean of x2, which naturally requires x2 and y to be linearly correlated. But in reality, we can actually predict any function on x2 given x1. Because this phase, we are learning from unlabeled samples, and you can do complicated stuff as you want, or even to learn the probability of x2 given x1, or their joint probability. Then it gives us, remind us of the traditional alternating conditional expectation method, which is to minimize over the psi x1, which is the same as before, minus eta x1. So instead of reconstruct x2 from psi x1, it jointly minimizes over both eta x2 and psi x1. So it finds the optimal connections between x1 and x2. And this is still reconstruction-based algorithm, and our previous analysis can actually apply to this form. But also interestingly, this kind of algorithm is actually equivalent to the following CCA algorithm, because like the quadratic norm of psi x1 and eta x1 are fixed due to the normalization, so minimizing over their squared norm is equivalent to maximizing their inner product in this case. But you can see that this form is really very close to SimSciM method. In that case, like x1 and x2 will just be two views of the same image, and psi and the eta will just be the representation function. But the only difference is SimSciM use stop gradient or like batch norm to prevent collapse. And here we use some normalization to prevent collapse. And like contrastive learning, they use negative samples to prevent collapse. By collapse, I mean like they don't want the representation to be constant among all the input. And also, we mentioned this because our analysis applied to the first case and they are equivalent to the second case. So our analysis can actually apply to this kind of SimSciM method. And let's see what they are. So by a little modification from the previous epsilon CI, we again can show the representation error scales linearly with this epsilon CI squared. Yeah, and also another interesting result is if x1 and x2 can both predict y very well, which means the base error is small, then we can show that representation error is upper bounded by this base error alpha divided by 1 minus epsilon CI squared. In this case, we don't actually need their remaining mutual information to be very small. We only need it to be smaller than 1. So notice that this kind of normalization ensures that epsilon CI is in between 0 and 1. And as long as y has captured some important mutual information between x1 and x2, it is surely smaller than 1. And in reality, the base error is very small because given the image, you can almost surely tell what kind of class it is. The base error is almost 0, so the representation error is also very small. And let's omit some experiments. And in conclusion, in this talk, we have investigated some sufficient conditions that guarantee that we can learn some good feature representation that can not only help us reduce sample complexity, but also can learn from unlabeled data and can even transfer to other domains with covariate shift. So this part is mainly from the first part of the talk. We haven't talked much about what will happen with self-supervised learning and what will happen with like modal shift. Some other possible direction is like how to learn invariant representations that can reduce spurious features or capture the causal features through like data annotation or input consistency, such that it can guarantee a good out-of-distribution generalization, and also possibly to learn some disentangled representation for explainable AI, and also adaptive-based meta-learning. So previously, we are using the representation as a fixed feature. However, it's also curious. We are also curious to learn how it works if we fine-tune the whole network. And this is actually already done and published in this year's Europe's paper. And also the role of representation in reinforcement learning is also a very important direction. Yeah, that's it. Thank you.
All right, so thanks, Dr. Chi, for the nice presentation. Is there any questions according to her presentation?
She also have a question about, it's a general question. It's for lowered the estimation error, you want to have the more label training data as much as possible to reduce estimation error. As you show in your slides, maybe it's the training data, the number training data is just in the decombinator. But from the perspective optimization, maybe you have to set up our parameterization setting. But at that time, it needs billions of model parameters. Maybe I think it's a contradiction between the number of training data and the setup over parameterization. How to deal with such a conflict? It's my general question about your upper bound, but it's also concerned with the optimization method and setting of neural network. It's a general question about it.
Oh yeah, thank you for the question. So basically for this result, it has no contradiction at all. So your prediction, your precise one can have a large optimization dimension, output dimension. But in this case, the cardinality of y is not mirroring the how many parameters you have. So I don't see any.
Oh, that's okay. I don't think it's very related to the second part. I want to discuss with you a general question about this deep learning theory. It's a general question.
Of course, yeah. As I said, that if your number of parameters is very huge, usually we will measure it by the weight norm, not the number of, not from the parameter counting.
Mm-hmm. So in the first part, you don't consider the optimization at all. So just to show the upper bound of this estimation error, this gives a mathematical formulation, right?
Right. So all the result is about statistical learning theory. It has nothing to do with optimization.
Okay, I see.
All right. Any other questions?
Hello, could I ask a question about the assumption of conditional independence? So why does it make sense, especially like in the setting of sim-sum? Like, why can we assume like x1 and x2 are independent conditioning on y?
Right. So as I mentioned that x1 and x2 are independent given y. This is a warming up result. It's not the main result. It helps us to see a very clean result that how it can work. But actually, our assumption is like x1 and x2 are independent given y and more fine-grained information. Like in your case, like in SimScience, x1 and x2 are like augmented data. Like if the augmentation is very, very strong, then so what it shows is actually if your augmentation is strong enough, the result will be better, right?
Mm-hmm.
So the stronger, so this kind of result shows you the better you satisfy this kind of assumption, the better your result will be.
Okay.
Yeah, and actually, this kind of result applies. So our standing point of the talk is about reconstruction-based self-supervised learning. So, so in the beginning, we are not trying to view x1 and x2 as two views of the same image. Yeah, and for the second part, I guess this part of result makes more sense. We don't actually require that the remaining mutual information is very small, but we only need this y to capture some important directions of the shared information between x1 and x2. That's enough. Yeah.
Okay. I see.
Actually, you have a very good question. So yeah, this is it's worth to clarify it.
Thank
you. Basically, our result indicates like if we want to get better result, we will hope that x1, x2's mutual information will be smaller given y and z, given the label and some other fine-grained information. And of course, like in this original context encoder paper, if x1 and x2 are very simply divided like this, then of course on the edge part, they will have some inevitable mutual information that is irrelevant to y, and we don't actually want that. And that's possibly why their original work doesn't work so well. But you see, like in the recent state-of-the-art result, what they are doing is that they also shuffle the images so that their connections will be unclear. So I guess this is kind of also aligned with our result. So basically our result shows the better this kind of assumption is satisfied, the better result we will get. So not that every pretext task really satisfy it, but we should actually like make sure it happens. Yeah, thank you.
All right, so we allow final questions. Pingyu, do you have some questions?
No, I'm very happy to see the result. I can reach out to Chi if I have further questions.
Sure. And all right, so thank everyone for attendance, and thank the CSIP staff, Janeta and Raquel, for try to organize the talk. All right, so have a nice holiday. Over.
Thank you. Thank you for the organization and everything.